Good morning, everyone, and thank you for your time and attendance this morning. We would like to provide you with the knowledge and expertise of our Swagelok Local Sales and Service Center, as well as let you know Swagelok globally as a company is here to support and deliver the same services we had prior to these challenging times. We will begin our session at 10 a.m. sharp, so I just wanted to give a 5-minute intro prior to our session beginning. Thank you, and we will start up right at 10. Good morning again, everyone. We will just give people a couple more minutes to join and we will begin at 10 a.m. Thank you again. Good morning and welcome to our Level 2 Regulator virtual training session. I'm going to do an introduction of myself. My name is Katie Whitman and I am the Marketing Specialist for Swagelok Southwestern Ontario. I joined our distributorship approximately 7 years ago, beginning my career as a CSR and then moving into some warehouse support. And for approximately 4 to 5 years, I have been supporting us as a marketing representative. I would also like to speak a bit about our local distributorship. Swagelok Southwestern Ontario services the Sarnia area, as well as Windsor and Essex County, leading all the way east to Hamilton, Burlington, Oakville, and as well as we cover the Niagara region and up to Bruce County. The core industries we cover, but are not limited to, are chem, petrochem, refining, steel making, power generation in both nuclear and fossil fuel, semiconductor, and automation. I'd also like to give a brief snapshot of our product offerings, but certainly we are not limited to our tube fittings, valves, hoses, quick connects, and today's subject, pressure regulators. We have also branched into services about 15 to 20 years ago when we began our custom solutions offerings, which would include panel assembly, skid fabrication, and sub-assemblies at our local shop in Sarnia. We also have a field services component in our services, which includes compressed gas leak detection, hose evaluation, and sample system evaluation services. I will now pass this over to our field engineer, Rich, who will perform our presentation this morning. And once again, thank you, everyone. We really appreciate your time this morning.
Thanks, Katie. Katie, can you hear me okay?
Yes.
All right, good stuff. All right, good morning, and welcome to everyone who's joined us this morning for our second session on regulators. I am Rich Wubbs, the field engineer for Swagelok Southwestern Ontario. I've been with Swagelok quite a long time, since 1997, starting at the factory that we had in Niagara Falls, Canada. Spent time as a manufacturing engineer and applications engineer in our biofarm services company, and for the last since 2008 been working with our customers here in Southwestern Ontario with their custom solutions and field engineering challenges. As Katie mentioned, we provide a number of services that can help you be more successful in your operations. And those services come through the field engineering team typically. And the field engineering team is a worldwide team of field engineers. We have over 100 of us all together. And the really neat thing about the field engineering team is that we can share our experiences and solutions to challenges with each other across the globe. So it's very easy for me to reach out and ask for some knowledge transfer on a challenge or solution that the other field engineers have experienced. So this translates into some really good solutions for our customers. Some of the services that we do provide to our customers: on-site evaluation of sampling systems, both grab sampling and online analyzers. In fact, the photographs you see here on this slide were from a grab sampling evaluation that we performed. This gentleman here, right here, that's myself. So now you know what I look like in my FRC and safety gear. So in these evaluations can be as simple as just a walk through your facility and having a look at some perhaps challenge areas and going over some best practices, and as complex as a week-long 4-person team, which these photographs show. One of the things that we have now as a challenge is COVID-19. So rather than send an entire team of folks out to a site, what we are doing is we'll send a limited number of local folks to that site, and then either have them do a virtual tie-in of others off-site using a virtual headset, or they will bring that information back to the off-site folks, and we'll work together on generating that report. So we've continued to do these assessments, and it's been actually quite successful and interesting to do them in the virtual environment that we have today. So this is our advanced regulator training. If you missed our first session, that training is available via a video, and we can provide that link. Just reach out to your sales and service center associate, and they'll help you with that. Some general housekeeping. Today we're using Teams live event for this presentation. So your microphone and your camera are not available to you. If you have questions, please use the chat feature. We do have folks looking at that chat, and they will either answer the questions directly or funnel them towards myself. And last but not least, thank you very much for attending the presentation. We appreciate having the opportunity to share this information with you. So today we're going to look at modifying the performance of your regulator, especially improving droop. If you recall, droop is the characteristic of a regulator that causes the pressure to drop as the flow increases. So we'll look at spring rates and dome loading, and then we'll look at flow curves and some best practices as far as understanding how a regulator will function in a particular situation. A little bit of review from the last presentation. The question, what is a pressure regulator, may seem a basic question, but it's important to realize that it's a mechanical device that's designed to control either upstream or downstream pressure, and it responds to system changes, such as flow, pressure, and temperature. What's important to realize is that a pressure regulator, it controls pressure. It does not control flow. So it will modulate flow in response to pressure requirements, but in and of itself, it is not a flow controller. You can't set it to a certain flow. It is going to respond to flow demand and open and close to maintain pressures. So that's a really key takeaway, is that while flow gets modulated, it does not get controlled. It's the pressure that gets controlled. So we talked about the balance of forces in a pressure reducing regulator. You'll notice that a lot of times I would call this a forward acting regulator, and simply that means that we have high pressure on one side and a controlled low pressure on the other. The balance of forces equation, that we have our set spring up here, our range spring. Whatever setting we apply to that, these forces down below, the outlet pressure force, our inlet pressure force, and our poppet spring force will be equal and opposite to that once the regulator balances. Similar with the back pressure regulator, we'll have a balance of forces. You'll notice this back pressure regulator lacks the poppet assembly that the forward acting regulator has. There are back pressure regulators with poppet assemblies in them. This image simply is a regulator that does not have that poppet assembly. So in our last presentation, we talked about these performance criteria. We talked about droop, which we'll look at a lot more today. Choked flow, that maximum flow you can get through the regulator. Creep, what happens to a regulator when it's shut off, but there's some contamination on the seat, where the pressure increases on the outlet. Accumulation, which is the opposite, well, similar to droop, but for a back pressure regulator. Lockup at zero flow, Joule-Thomson effect for temperature changes through a regulator, and the optimal flow part of the curve and supply pressure effect. So today, though, we're going to focus on droop. So the challenge that we have with a regulator is that the reality of the matter is that we have a certain flow and pressure that we have in mind that we want to operate at. However, the reality of the situation is that our processes are going to work over a flow range. but we still want to maintain that pressure over that flow range. But the reality is that while this is the reality, this is what we want to do. The challenge is that our device is going to follow, our regulator follows this flow curve. So it becomes a challenge of how do we set this device in order to operate well for us. So we could choose to set our regulator at this point here, which is our lowest flow, and we set it at our target pressure. The challenge in this case becomes that as our flow increases, as we go along here, we're okay, and we're still kind of okay, but by the time we get to these red dots, we've fallen below our pressure requirement. So setting our regulator here at our lowest flow is not appropriate in this case. Similarly, if we would set it at the highest flow, as our flow decreases, our pressure is going to increase to a point where it's no longer acceptable. So that's not optimal in this case. So we could set it out here at just the start of flow, but then we've got our no pressure that is acceptable high enough for our operating conditions. So it's really a challenge. We could certainly set it to the middle, which is the best practice, really. Set your pressure at the middle of your flow range, but maybe that's not good enough. In this case, now none of our pressures really meet what we intended to do with our process. So in this case, we really need to come up with a different way of managing our pressure over our flow. We really need to flatten that curve. And that really means to change the device's characteristics. So this characteristic line here is how the device works. So we really need to go to a different device in order to get this flatter curve. And what I mean by different device, I don't mean a totally different system. I mean a regulator that has a different internal mechanism to it. So let's just review why that flow curve exists. So we have our balance of forces equation, and F1 here, that's our set spring. F3 is our outlet pressure force. When a regulator is balanced or near balance, if our inlet pressure stays the same and our poppet spring force is not going to change by very much, so we assume that those are simply fixed numbers in this equation. That means that whatever F1 does, F3 is doing, or vice versa. Whatever F3 does, F1 is going to be following suit. So here's what happens when we have our flow demand increase on the outlet side of the regulator. What happens is this poppet here, in order to allow more flow, it needs to move down. When it moves down, this loading plate is moving down, which means that this spring here is extending. So this spring is actually losing some of its set force. So, and this is what's driving. So since our set spring is losing a little bit of force, our outlet pressure is going to lose a little bit of force in order to balance out. So since that's the case, and it's our spring that's creating that situation, what could we do to modify our spring to make that situation different? Well, here we have an example of a short spring and a long spring. this short spring is typical of our KPR instrumentation regulator, whereas the longer spring is typical of our RHPS process type regulator. The shorter spring has got twice the spring rate of the longer spring, and we're going to look at why that's important or has an effect right here. So in order to get the same set force on each of these springs, the longer spring needs to be compressed by twice as much, so 16 millimeters instead of 8 millimeters. So for every unit of length change on this spring, you've got half as much force change on this spring as you do on the shorter spring. So if our valve moves, so if in this case, if the poppet moves down by 2.5 millimeters, we're going to lose 1,000 newtons on this shorter spring, while we only lose 500 newtons on this longer spring. So ultimately, what that means is that for two regulators with the same control range, we're going to have a droop of 3.2 bar on the shorter spring and 1.6 bar on the longer spring. So by using a spring rate that is lower and a longer spring, we get a much better droop performance. It flattens that curve out. So that's one way of flattening the curve. Another way of flattening the curve is to replace our loading spring with a compressed gas. We call that dome loading. And what we discover is that the dome loaded curves are super flat. On the left here, you can see we have 90 SCFM as the right-hand side of this chart. On the right-hand chart, 90 SCFM is just here. So we actually, this chart actually has a factor of 10. It's 900 SCFM at the extreme end here. And just look how flat these droop curves are. So that's the advantage of dome loading. We take away the spring rate that is involved with this mechanical spring. So I'm gonna go back to that slide for a second. So you may be looking at this now and saying, "Oh yeah, well, dome loading is the way to go, like every time," and that's not true. The spring-loaded regulator is an excellent regulator. It's an excellent fit for a lot of applications. So the spring-loaded regulator it's a very good device. But it needs to be applied properly, and it needs to be understood that it follows this curve. The dome-loaded regulator comes with more mechanical complexity as far as support for the regulator. We need to provide this supply pressure, pilot pressure. The system becomes more complex and more costly. So, as with any engineering type of situation, the decision is going to be cost versus functionality. We always want to choose the most cost-effective solution for the challenge that we face. And the spring-loaded regulators have got they're excellent. They've got a really good place in our systems. So with a dome-loaded regulator, typically you will have a pilot regulator. So and thus the added complexity. Now, yeah, you may be recalling our previous slide, and we just got rid of a spring-loaded regulator, and now, hey, you're putting a spring-loaded regulator back in here. So the question sometimes is, well, doesn't this regulator cause droop once again? And the answer is no, it doesn't, and here's why. This pilot regulator is set up to provide pressure to this dome. So we have our inlet pressure on this side. We have our downstream pressure on this side. The dome loaded unit is being fed our pilot pressure here. But then we have a bleed off that comes back into our downstream, and it's got an orifice plate in it, so it limits flow. So this regulator, this pilot regulator, we have this because we have this flow orifice here. It's going to see constant flow or nearly constant flow. So once we set this regulator to a setting, it's going to stay there. Yes, it's subject to supply pressure effect. It's also subject to droop. However, by setting it up off the side so that it's basically in its own flow loop, we set that regulator up so that it's got its best chance of staying in a small zone of that curve. So this regulator itself will not be subject to any significant droop characteristic, and so then we gain this wonderful ability of the dome loaded regulator to perform over a wide series of flows. Now that we've looked at the theory of it, let's look at some of the practicality of the how does that dome loaded regulator actually work. So when we have no pilot pressure up here in our dome, we will have this poppet is going to be shut, and we will have the same no pressure situation here in the sensing chamber. When we apply a pilot pressure to the dome chamber, that's going to drive our poppet down, and we're going to open up to flow, and that flow will continue until we reach a balanced situation of 5 bar above and below our diaphragm. So this is a setup with equal areas on both sides, so we will balance out at 5 bar. At that point, the poppet closes, and the regulator waits for downstream demand. Once this downstream demand depletes this 5 bar, we will open up again, and this regulator will balance itself out at at whatever flow rate is downstream, and continue to flow to balance that downstream. So here's another representation of the piloting setup of that dome loaded regulator. You can see here that we have our pilot regulator with the spring. We are taking its supply pressure off of the main supply pressure to the main regulator, and providing that to the dome in a flowing situation, a constant flow situation. You can see here in the construction of this dome that you've got a support plate behind the diaphragm. So this is to prevent the diaphragm from extruding itself like a balloon through this cavity. The dome pressure makes its way through that support plate through these holes. So, and down here in the process stream side, we have our inlet pressure coming into our poppet zone. This is a balanced poppet where we've got our outlet pressure underneath the poppet and above the poppet. So there's a drilling in the poppet that balances it. This helps with the droop characteristic as well. And similarly, we have, as in the top, we have these flow channels. We have flow channels through the bottom plate as well, the guide plate for the poppet assembly. As I've mentioned, we do have a flow orifice in the system that manages flow. So that's something important to keep in mind, that if you're ever working on a dome-loaded regulator, somewhere on this setup, you will find a flow control orifice. So that's something to keep in mind. We always put it here into the body in this body fitting, but more often than not, it's machined into a fitting, and you need to be careful not to mix the fittings up, or at least be aware that one of the fittings will be different. So that's managing droop in the in regulators, and some of the ways that we can do that. Were there any questions that came through the chat that we could answer right now?
Rich, we have not had any questions as of yet. So if anyone does have any questions, please use the Q&A and we'll address them as soon as we can. Thank you.
All right. So then we'll move on. We're going to talk about flow curves now. And what I want to do is want to first go to the swagelok.com website with you and just show that if you type regulator in the search box and click on resources, we've got some really good resources here besides product catalogs. We have some good white papers, and what we're looking for here is this pressure reducing regulator flow curve technical bulletin. So this is the information that's in here is what we're going to be digging into in our next slides. It's got 216 pages. Don't be daunted by that. Most of those pages are not text. They're simply charts, and it's very quick and easy to hone in on which particular pages you need. There are some good explanation pages here of the different characteristics and some of the manipulations you can do with the curves. The nice thing is you can very quickly, if you're looking at a KPR regulator, you can very quickly get to gas flow or liquid flow curves, or a KPP, same thing. So we've got some nice links here that you can jump to that particular part of the catalog, not catalog, the technical bulletin. So we're going to go through some details on the flow curves, the layouts, how to read them, and how to manipulate. Okay. So the first thing you're going to notice on our flow curves is that there's multiple curves on each chart. And the reason for that is it's really twofold. First of all, so you can compare similar or the same regulator with different characteristics. As well, if we made a single chart for each set of lines, we would have had 600 pages or more in the catalog. So the blue lines here represent our 0 to 250 control range. The black lines would represent 0 to 500. So this is the regulator pressure control range. So that is the actual pressure control range that is part of the regulator's makeup. All right. So when you select a regulator, in the part number, if it's a 250, you want to follow these curves. In the part number, if it's a 500, you want to follow these. The next aspect is going to be inlet pressure. Now, this inlet pressure is the actual inlet pressure that the regulator will be fed. So in this case, it's not the catalog rating. This is the actual inlet pressure. So and you'll see we've got letters next to our various lines. So here we've circled J, which is our 500 psi inlet pressure. And you can see that this curve here has got a J next to it. Similarly, so these three curves correspond to having 500 psi in. What's interesting about that is you can really see here. So this set of curves here at the bottom of the chart is for a 0 to 250 that has been set at 100 psi at zero flow. And you can see that when you only feed it 100 psi, the droop curve is super steep, whereas when you feed it, over 3,000 psi, the curve becomes quite, flat over this range of flows. So it's quite a big influence over the operation of a regulator is what kind of pressure you're feeding it. So next we have outlet pressure, which is our vertical axis. And you'll see that it's PSI on the left and it's bar on the right. So whether you're working in metric or imperial units, the charts are very easy to read. Similar for flow, SCFM on the bottom, and standard liters per minute on the top. Very, very easy to move from one to the other without having to do a calculation. Okay, so we're going to go through some examples. This is really the best way to become comfortable with these charts. So this first example, we're going to be looking at the 1,000 psi inlet pressure. We've got a nitrogen flow, so that's important. The type of gas that you've got flowing through will change the way this axis behaves. So all of our charts are done in nitrogen. In this case, this example is nitrogen, so a nice starting example. Our flow rate is 25 SCFM, so right around here. And we've already circled our 1,000 psi curves, letter L. And our pressure, our setting, is going to be 175 psi, so somewhere around there. Okay, so when we project our 25 SCFM line up, the second curve that we hit, that's for the 1,000 psi inlet, is going to come across at a little over 200, maybe 210 psi. But we know that we're going to be setting the regulator at 175 psi, which is right where that this purple shading ends. So the interesting thing is, what we can do is we can actually shift that line down, so this line here, where it right now it's up here, we can actually take that and we can shift it down, and my ability to trace today is not as good as it is on other days. This line here should look like this one here. So we can shift this line down, and we know that it's going to perform similarly with the 1,000 psi at a lower set pressure, and we know that droop curve applies. So we're going to look at another example here, and again, at any time, please send questions through. I've got a number of examples here, and if there's a question, we can always go back to one of these and dig a little bit deeper. So this next regulator here, the question that is asked here is, what is our pressure drop? So droop and lockup for this LRS4. It's got a 1/2 inch inlet outlet on it. When the flow increases from 0, so from lockup, to 150 normal cubic meters per hour. Okay, so this chart here has got normal cubic meters per hour at the top, and it's got SCFM on the bottom. So something important to note is that when the charts have got normal cubic meters per hour at the top, see how the order of magnitude of the numbers is very similar to what's on the bottom. So you really have to be careful with charts with those two scales on it, not to use one instead of the other, especially if here's 150 and here's 150. Easy to make that error. So first of all, I want to find the correct flow curve. All right, so our inlet pressure is at 507 psi, so we know it's going to be one of these that's tailing out here. In this case, we have a set pressure of 250, so we know it's going to be that curve that we just pointed at. All right, so we want to find 250 psi at our start, which is 0 flow. Conveniently, that is right there. Next, we want to find the point on the flow curve for 150 normal cubic meters per hour. So we want to go from that top scale and drop down and find where it crosses the curve. And then we're going to move that across to our pressure scale, and we can read the pressure, which is around 220 psi, and we take the difference between the start and the end pressures, and that's droop. So the difference between those is about 30 psi. So the answer to the question, what is our droop and lockup for this particular regulator? Our droop and lockup is 30 psi. And if you wanted to know what that was in bar, you could look at the other side here, and you would conclude that it's about 2 bar. So that's a typical way of using a set of flow curves. Once you have settled on, okay, this looks like the regulator for me. Now we dig deeper on that curve and see what it does as it performs in its range. So, and that's how we use the flow curves bulletin. Is we know what our theoretical set point of pressure is, and what flow rate, maybe flow range, and we start looking through our flow curve technical bulletin to find a set of curves that fits. And once we find and usually there's 2 or 3 curves that will fit, maybe even more, then we start to look at these particular details of what happens when and if this happens. So once again, now we're going to look at an RS10, and the question is, what is the outlet pressure at 580 SCFM when we set the pressure to 125 at 400 SCFM? Okay, and 1015 inlet pressure. Okay, so this RS10, it is a spring-loaded regulator, so still a fairly good slope to the droop curve. So We look for our nitrogen flow of 400 SCFM. So we want to make sure that we're using this scale down here. So we're setting our pressure at 125. So 125 is around here. So we're going to need to move a curve down. And we know we're at an inlet pressure of 1,015. So we're going to take that curve there and we're going to move it down. Okay. All right. So so here's our start point, and we have our outlet pressure at 125, and now we're going to look at our increased pressure or increased flow of 580, and we can shoot across there, and we can see that now we're at around 120 psi. And that's around 8 bar. Oop. Let's get through that there. So yeah, so our the question was, what's our outlet pressure when we set our regulator at 125 and 400, and then have the flow increase to 580. The flow has increased and our pressure has decreased from the set point of 125 to around 120. Okay, so now we're going to go to this LPRS10, so a low pressure regulator. And now the question here is, what will be our pressure at no flow? So we've got an inlet pressure of 15 bar, and we've got a dynamic, so a flowing pressure of 2¼ bar at 500 normal cubic meters. Okay. So we first of all put our line across at 2¼ bar, and we look at our 15 psi inlet pressure line here. So we are right here. So what we need to do is take this curve here and we need to move it so it lines up with that point right there. So in this case, we're representing that moved line by this straight line. I apologize, it doesn't have a curve to it, but it is a good representation of what is going on. It has similar slope. One thing to note is that it's okay to move these lines down towards the 0, 0. It's not okay to move them up. Moving them up isn't effective because there's mechanical limitations inside a regulator that come into play, that when you try moving a curve up, it's just not reflective of what the regulator is doing. But to move it down is quite reflective. So in this case, we have our dynamic, so it's flowing 2¼ bar, 500 normal cubic meters. So 500 and 2¼ bar. Our curve is going through there, and the question was, what will be the pressure at no flow? So this approximated straight line that we have here, it looks like it is going to cross at around 40 psi, or in bar, that's going to be right around here, so probably 2.75. Okay, so that is our lockup pressure is 2.75. So that change in pressure was ½ bar from our 2¼ to the 2.75. So ½ bar, well, 7.5 psi. Okay. So now what we'll do is we're going to look at a dome-loaded regulator. It's got the D in the part number. But we're also going to change things up a bit. So all the other curves that we looked at, we were looking at nitrogen. So that made it easy because our curves are done in nitrogen. But now we're going to look at hydrogen. Really, really light molecule. So we've got this 3,800 normal cubic meters per hour flow. The temptation might be just to look at the chart and go, well, we've got, okay, 3,800s here. Oh, that's way out there. You need to resist that temptation because hydrogen and nitrogen, these scales are vastly different. So we address that in the flow curve technical bulletin. There is on page 4, we have an explanation and formula that show how to adjust the curves based on the gas's specific gravity. So that's what we're doing here. Is when we do the run through our conversion calculation, we discover that there's a correction factor from nitrogen to hydrogen of 3.8. So it results in a 3.8. So whatever happens on this scale here, we need to multiply by 3.8. So that means that 3,800 normal cubic meters of hydrogen is going to have the same flow characteristic as 1,000 cubic meters per hour of nitrogen. So this is 3,800 of hydrogen. Okay. So the question was, what's going to be the droop at this flow? If we set our static pressure at 30 bars, that means zero flow. All right, so at zero flow, we're going to have 30 bar. All right. And that's our 3,800. Okay, so there's 30 bar, zero flow. We're going to take this curve, we're going to move it down. There we go. All right. We're going to then look at where it's crossing here, and that's going to tell us our pressure at that flow. So we see that now we're crossing around and having that droop be about 5 bars. So it's around 25 bar right here. So we've dropped 5 bar. So similar to what we've done on all the other curves, the only wrinkle here was that we utilized our correction factor, because we realized that hydrogen is going to flow at a much higher rate. The hydrogen flows at a much higher rate than nitrogen for a given set of circumstances. Ultimately, the most important thing to know is that the correction factors exist, and that what you're doing is multiplying this scale by the correction factor, whatever that is. And I find it's best to actually write the scale above. So I would write 3,800 and all the hydrogen flows above this scale, and work with it that way. So typically what I'll do is take our flow curve technical bulletin and using a PDF editor, put lines and notations on it in order to not only work my way through the process, but also have a document to refer to in the future. So those are all the examples that I have of flow curves and how to use the flow curves. We already looked at this flow curve technical bulletin. There is one other interesting tool that we have on our website. If I go back to swagelock.com, and easiest way is, I'll just go back this way. There we go. All right. We have this toolbox link, and we've got some really nice tools here. So this is, again, this is swagelock.com. We have CAD files and sales drawings. This includes 3D models of the bulk of our product line in various formats. So it's really handy for design. Certifications, you can access CRN documentation there. We have a CV calculator. So you know your pressure and flow, or your pressure or your flow and your pressure, you can find out your CV required, or vice versa. And here we have our regulator flow curve generator. And so this generator, it's got some limitations, so you do need to read through this page. So please do that before you click the green link that gets you there. And once you get here, the nice thing is with RHPS regulators, you can compare up to 4 regulators, and you can put in the information for those 4 regulators, and the curve generator will, once you get to the bottom, you hit calculate, and it outputs a nice set of curves. And I did this earlier today. Did this set of curves. So basically, and this was for 3 separate regulators. And I thought it would be interesting for you to see. The nice thing with this is that rather than have a the static set of curves that are in the flow curves technical bulletin, where you really need to manually move the curve down, you can set your parameters so that you get this flow curve. In this case, your initial setting was 40 psi at 0 flow. Well, you could actually say, yeah, I want 40 psi at 25 SCFM. So I'm going to adjust the parameter I put into the data page. I'm going to adjust it up by 3 psi. I'll put 43 in, and you can have that curve cross right at that 25 SCFM. So here I did 3 regulators for this example, and I did the same regulator, an RSH4, with and what I did is I varied the inlet pressure. Okay, so outlet pressure of 40 psi in all the cases. So I varied changed the inlet pressure from 250 to 500. All right, so you can see that here. We have our 250 here, our 500 is here. And then, so those 2 were for nitrogen. And then the third one I did for helium, just to see what the helium curve would look like. And I did an inlet of 500 psi. You can see how much more flat that helium curve is, for that nice small molecule that flows nicely. There is one interesting thing that I want to point out on these curves that's different than anything else that we've looked at through the rest of the presentation. We have this line velocity line here. So these 2 here. And what those line velocities represent is so over time, gas handling folks have developed empirical knowledge that says that at certain line velocities, so that's the actual velocity of your fluid flowing through your device or your pipe or your tube. When it exceeds a certain velocity, that it starts to create noise. So over time, they've empirically observed that when you get beyond that velocity, you hear noise. And that's what this line is representing, is that ideally, if you don't want to have any noise coming from your system, stay to the left of these lines. The device will work to the right of the line. However, there's a chance that there'll be noise. So this is one of those things that it is worthwhile considering and thinking about as you specify a regulator. And it's something that per application we can discuss more deeply when that application comes up, to ensure that line velocities are don't become a problem. And sometimes it's as simple as, this is a half-inch inlet outlet regulator, that we take that inlet and move it up to 3/4 inch, and that'll move that velocity line out, because as you upsize your line size, for the same volumetric flow, your velocity decreases through that line. So to review, the droop performance, is the thing that we look at the most and has the greatest effect. It also is the most noticeable thing for end users. For spring-loaded regulators, that droop is directly related to the spring rate. So longer spring means less droop on that unit. And we can improve our droop by making that spring longer, or choosing a dome-loaded configuration and then tweaking that dome-loaded configuration to give some better feedback and control. The flow curves, those allow us to pick the right regulator for the job and look at what's going to happen as far as pressure drop, lockup, and the droop profile over the flow range. And we now know that we can pull curves down, that the inlet pressure will modify that droop profile, and that we need to adjust our flow axis for our gas type. So I'm hoping that this information has demystified those curves for those in attendance today. I'm sure there's questions. Do we have questions in the chat? If there aren't any questions in the chat, please be sure to get in touch with us with any questions. So Katie, do you?
Yes, Rich, we do have a few questions. I'll start in order. The first question that came through is it always best to have a low spring rate, or does that affect response time or price to a considerable amount?
So the answer is it depends, and it really depends on the application. So the larger you make a regulator, just the more it's going to cost. There's a few trade-offs that happen. So to get a longer spring, you need to have a larger regulator. Hence, the regulator is heavy or heavier, and it takes up more real estate. So you may not have the amount of space in your setup in order to accommodate this larger, heavier regulator. So if you don't need the larger, heavier regulator, it doesn't make a whole lot of sense to go towards. It really needs to fit your application. So if you need a smooth response of low droop to a range of flows, then you may need to go and use that longer spring regulator. However, if your flow is typically if your flow band is typically fairly narrow, and the amount of pressure variation over that narrow band is acceptable, then I would start with the smaller, more compact short spring regulator. What's our next question?
Our next question, I actually responded. It was just, if we have difficulty choosing the correct regulator, can we contact you for technical help? And I just responded with absolutely. Your sales rep is always available for technical assistance with product selection.
Yeah.
So that should be fine. And then we had one additional question, and it was, if the flow makes noise, is that affecting the seat and seals?
So it all depends on where the noise is coming from. So yes, noise is an indication that there's something going on, and it certainly could affect the seat and the seals. The bigger concern with the seat and the seals is chatter. So if you're going to work in the lockup zone, so very, very close to that zero flow situation, you can get a chatter that sets up as a high frequency noise. That's fairly damaging to a regulator over time. When you're talking about maximum line velocities, it really has more to do with the velocity at the outlet of the regulator. So you have to imagine when a gas comes into a regulator, it is its density is higher. So for so your mass flow into a regulator and your velocity into a regulator and up through the seat is fairly low. Now, once you expand across the seat, you take that mass flow and you expand it into a larger volume. Now suddenly your velocity increases by a lot. So it's really at the outlet of the regulator, where there really isn't a seal, that you run into that velocity noise that's defined by that extra line on the chart that I was showing you. So you really have to look at, okay, am I in a high flow situation or a low flow situation? Low flow is likely chatter, which is probably going to cause you some mechanical trouble inside the regulator. When you get to a high flow situation, assuming that the regulator isn't working at a choked flow situation, then more than likely that noise is coming from somewhere away from the poppet and not likely causing the poppet issues. But your people working around that device may not appreciate the sound coming from it. So that's noise in a regulator. Do we have any other questions?
That's all we've had, actually, Rich.
Okay. All right. Then I'd like to thank everyone for joining us today. We really appreciate that you took the time to learn more about regulators. And as Katie said, we're always available to help. And if you have any questions, please reach out to your sales associate or myself or anybody else in the organization. And please go ahead to swagelok.com and have a look at those neat tools that we have available. They really are handy tools. I make use of them myself regularly, and could help you use those tools as well. So with that, we will bid you a good morning and have a great rest of the day.